In the previous video, we have talked about different ways to describe or characterize how connected a network is, mostly focused on the whole network. And in this video, we're interested in analyzing the positions or importance of every individual node in the network, which can be meaningful and useful for thinking about influence, importance, of those individual nodes. So it's focused on a different level of the network, which is nodes. And then the measures we're going to use or introduce in this video are measures of no importance, which includes degree, closeness, centrality, between centrality, page rank, and so on, which are capturing different kinds of importance as we consider nodes in the network. In the process, we're going to learn different ways to, the assumption behind every measure, because every measure is different, it's capturing different things, different kind of importance. There are assumptions made for every measure, and also how to calculate them, both using, manually in some cases, and also more conveniently using network X, because the power of network X is it provides a range of functions for you to leverage to quickly calculate those measures. So let's get started. So in terms of node importance, it is one important concern in social network analysis because we often ask this question, which is based on the structure of the network, which nodes are important, or which are the most important nodes that we want to identify? And this question can have direct applications in many cases. For example, if I'm trying to spread a piece of information in a network, where should I start? Should I start from people who has the most connections? Should I start with people who has very short distance with everybody? Or should I start with somebody who is gatekeeping in this network? So those are different ways to think about this action of spreading information in a network. And every approach I take kind of reflect a particular definition of importance. So for the demonstration purpose, we're going to use this data set we have mentioned earlier, which is a karate club network. We load that directly from network X. This is how this network looks like. As we think about network importance, one of the most important measures in social network analysis is to think about centrality. And centrality measure, they can be used to identify the most important nodes in the network. As I mentioned, there could be many examples. Just add a few more. We can think about networks that are hubs in a transportation network or in a computer network. We can also think about important pages on the web, which is actually what the Google search engine was built on, which is how to define the most important pages in order to return the most important links to the user. And also nodes that prevent the network from breaking down. That's another way to think about centrality and importance is if we take this node down or this network fall apart. This is actually used in a lot of anti-terrorism operations. In order to kind of fight against terrorism, you take out this most important actors in the network. So again, those are the broader application of the idea of centrality. There are different ways to think about centrality, as I mentioned. And here we start with the maybe the simplest among them, which is called degree centrality. And then the assumption behind the idea of degree centrality is this. It's about the important nodes. We assume they have the most connections. So the degree centrality is trying to capture those nodes. We define the centrality based on the number of degree or the number of connections every node has. And then the concept of degree is basically the number of neighbors that the node has. For undirected network, it just number of neighbors this node is connected with. For directed network, there are two different kinds of degree. One is in degree, that is about how many edges are pointing towards this node, versus out degree is how many edges are pointing outward from this node. So they're a bit different. just because there's a direction to be considered. So building on the idea of degree centrality is a little bit complicated, slightly complicated because it's trying to control for the size of the network, because the degree, in some cases, it depends on the size of the network. A larger network may have much larger degree because there's simply more nodes to be connected with. So degree centrality mathematically is designed or defined by the degree or the number of neighbors of a node we want to investigate, divided by the size of the network -1. And that's how it's computed. And the good news is in network X, you can directly call this function degree to get, to get the degree for every node. And then you can manually calculate every, the degree for every node. For example, if we take node 0, because the degree of node 0 is 16, and then we divide 16 by 34 minus 1, 34 is the size of a node, you get the number 0.48, which is degree centrality of node 0 in this network. Again, this is manually calculating, but using the measure degree. A faster way to do it using network X is using degree centrality. There's a function that you directly call, which will return the degree centrality for every node in the network. And here we just check the degree centrality of node 0. It is the same as our manual calculation, which is 0.48. And for the directed networks, as I mentioned earlier, there are two different kind of degrees. There are two different functions you can use to calculate in degree centrality and out degree centrality, respectively. But again, the idea of degree centrality, regardless of the direction of the network or the existence of direction in the network, is based on the assumption that important nodes have more connections, they have more neighbors. So using this measure, you might be able to find those nodes, based on the question you're asking, that can be considered important. But degree centrality is not only the only centrality measure we can think of. Another centrality measure that people think about is based on another assumption. It's based on the assumption that important nodes are close to other nodes, right? If the node is close to other people, not necessarily directly connected, but they're close to other nodes, we can think of them as important as well. And mathematically, it's defined by using the size of the network -1 and divided that by this the total of the length of the shortest path from this node we are interested in with other nodes in the network. And then, the number we get basically describes, given the size of the network, we have how far away in total this node is with other nodes. All right, so the node that is closer to all other nodes will have a bigger number. In this case, will have a higher closeness centrality because that forms the bottom part of this equation. And here you can directly call closeness centrality, which is another function in network X. You get for every node in the network, you get a closeness centrality, just the same as a degree centrality. And here we check the node 0, which has this number. And you can follow the same thing. You can manually calculate this by first calculating the total shortest path length. I know it's kind of a mouthful in terms of how much information every sentence has, but you can calculate the total of all the shortest path lengths between this particular node, which is 0, and all the other nodes in the network. You get a total, and then you divide the size of the network with that number, and you get the closest centrality manually. And I know it could be harder to kind of think through this slightly more complicated concept, but if we think about that, I think if we start with the simplest network, which is a triangle, if there is a triangle in which every node is connected with the other two nodes, right? The closest centrality would be 1, just because each node is 1 hop away from the other 2 nodes. And then if we think about a square, the closest centrality of every node will be 0.75 because every node will have, every node is 1 hop away from 2 other nodes and 2 hop away from the 4th node, right? Which is, in this case, every node, if we think about this node, is 1 hop away from those nodes in the middle and 2 hops away from this node further away. So this closest centrality for every node in this triangle, or sorry, in this square, would be the size of the network 4 minus 1 divided by 1 plus 1 plus 2, which would be 3 divided by 4, which would be 0.75. Right. So, starting from the simplest network you can imagine, you can kind of get an intuition of why closeness centrality is calculated in this way. And you can both, I think it's usually helpful to kind of manually calculate to get the number and then compare with what this package returns for you before kind of use the function directly. So again, closeness centrality is based on different assumption, which is based on the distance from this node with the other nodes in the network, and that's how it's defining importance. And there's another centrality measure, which is used a lot as well, which is called betweenness centrality. The assumption is different. The assumption of importance in this idea is that important nodes connect other nodes. Or in other words, for a node to be important, this node is connecting others. It's occupying the position that bridges the connections of other nodes, right? And then there are certain ways to calculate that, and I won't go to details, but I encourage you to think about it. But it's a very similar idea, right? You try to find for a particular node in how many occasions this node is on the shortest path between another pair of nodes, right? For example, if the node is very, in a very important position, for many other pairs of nodes to be connected, they have to go through this node, right? That's the intuition of betweenness centrality is other pairs of nodes need to go through this node in order to be connected. I won't go to mathematical details here just for simplicity, but you're encouraged to check out how it's mathematically calculated. But one important thing I want to mention that betweenness centrality in many cases needs to be normalized because the larger the graph is, the more nodes you will have. And as you imagine, the betweenness centrality can grow because a node can be on the path of more nodes if there are more nodes to be connected. So in network X, at least, you have a particular way to control for the size of a network, and which is to divide the centrality values by the number of pair of nodes in the graph, just excluding the considered node. Again, I'm not going to get into details there. But here I just want to mention, very similar to earlier centrality measure, you can call this function called betweenness centrality. And here I include this parameter, which is called normalized to be true. You'll get the normalized measure of the centrality betweenness. And using the same process, you can find out for node 0, the centrality, the betweenness centrality is this number. And you can also try to find, right, just for fun, find the top 5 nodes has the highest betweenness centrality, because you already have this betweenness centrality computed for every node in the network. You can start to sort this list, and then you just get the first 5. And here you see node 0 is still the most central node in terms of betweenness, and then followed by node 33, 32, 2, and 31, right? Hopefully this, again, gives you a sense of how important those nodes are, and based on betweenness centrality, those 5 nodes are most important. And finally, there's another measure of centrality, which is called eigenvector centrality. The mathematics is a bit more complex. The assumption is, it treats nodes to be central if the node is connected to other central nodes, right? So it's no longer about how many neighbors you have. It's about whether your neighbors are also important neighbors. That's the intuition of it, right? So I'm not going to get into the mathematical details of it, just for the sake of time. And again, using network X, you can calculate eigenvector centrality using this function. And you can do the same. You can find out the most important nodes based on eigenvector centrality. And in this case, we find node 33 is thought to be more important than node 0 because eigenvector centrality is capturing a different thing, right? You would kind of go back to the visualization. We can notice, right, the possible reason of that is for node 0, it is connected with a lot of nodes that are not connected, not very connected. They're more of on the peripheral. They're less important in the network versus network 33. Even though it has lower degree or lower degree centrality, lower between centrality, it seems to be connected with more nodes that are a bit more connected, right? For example, those nodes 33 are connected, they usually maybe have more connections. Or for example, 28, I just see that there's more density on this side where 33 occupies compared to on this side, node 0 occupies. So, that's visually, I can kind of infer, maybe that's the reason that 33 has a higher eigenvector centrality compared to 0. Even 0 has a higher degree or closeness or between centrality. But again, what matters for you depends on the question you want to ask, right? Which measure, we're providing you a list of options to choose from, and what measures matter for you depends on the question you're asking, depending on the context you are working with, depending on the nature of the data you are coping with. But one pretty typical use of those network node level measures is you can extract off them, and you can potentially fit those measures into additional data analysis pipelines. For example, you're trying to cluster students in a specific situation, or such as a discussion forum space, or you're trying to predict, build a predictive analytics. You're trying to predict whether a student will drop out. There might be some measures of centrality that can be used to help with that task, to help you engineer new features to help with the predictive analytics. So just to wrap up in this video, I want to demonstrate you can calculate all of those measures. You can, for example, starting from the data set we have about the karate club, you can create a data frame based on the nodes we have. This is very simple. We only have the ID of the nodes, and then we can extract different measures of the nodes. For example, we can extract degree of the node. We can extract degree centrality, closeness centrality, between centrality, eigenvector centrality, and then put them in the data frame. We can even include the attributes of the edges, of the nodes as well, because apparently there's a attribute named club that's used to describe every node in the network. And here, starting from this data frame, you can potentially do some more interesting analysis by looking across different centrality measures, or combining different centrality measure with other type of attributes of the nodes to conduct more interesting and more sophisticated analysis that can help you answer questions. So in summary, social network analysis provide a range of measures to describe the importance of nodes, but the importance or interpretation of every measure will depend on the context in which it's applied. It's very similar to measures of network connectivity. Those measures about nodes could be further enriched by considering direction, weight, temporality, which is not captured in this module. because it will be a full course to really dive deeper into those different directions. But hopefully with this introduction, or the slight introduction to social network analysis, you are getting ready to dive deeper into this area. And there's so much online information that you can consult in order to address any specific question you might have about a particular measure, or to think about different applications or a different combination of analysis you can do using social network analysis. I hope this is only the beginning for you to dive into this really rich area of research, and I hope to learn from you as well as we move forward. I'll see you in the next video.